Hi guys. Today we are going to try and solve a problem that was posted on the Wisent website, and it has to do with uncertainties. So let's go ahead and first of all look at the question, and then I have a few insights to share with you before we actually start solving the problem. But let's take a look at the uh, question itself. So the question says that the length and breadth of a rectangular sheet have been measured by a measuring scale to an accuracy of zero point 0.2 meters. Uh, and it says zero point 0.2 meters, which is the same thing as 20 centimeters. We want to convert that because the rest of the values are given in centimeters. Anyway, going on with the reading. If the measured values are 35.2 centimeters and 31.7 centimeters respectively, then find the relative error in area of the sheet. So important things to note here, relative error is what we are looking for. And it's the area of the sheet in which we are looking for that error. So those are the two important things to note here. Uh, And then, like I said, I was going to share a few insights about this this topic, this idea, and we'll do that before we start working on the actual problem. So, first thing is that you need to be clear in in the idea that there is no such thing as an accurate measurement. And when I say accurate measurement, I mean 100% final, definite, accurate measurement, which means that, yeah, you can measure things as accurately as possible. That is always the caveat that comes with accurate measurement, as accurate as possible. And the possibility changes depending on the person making the measurements, how well they are able to see, and there could be problems with the eyesight, there could be problems with concentration, whatever. Second thing is how accurate is the instrument that is being used, or in other words, uh, what is the least count of the measuring instrument. So, for example, if you are using a meter rule to measure a length, most of the time the most accurate you can get is to 1 millimeter. But if you're using a vernier calipers, you can get to a tenth of a millimeter. And if you're using a micrometer screw gauge, you can get to as accurate as 1/100th of a meter. But then if you use a laser measurement, you could get even more accurate. And so what is important to remember is that with the advent of better and better technologies, the ability to measure accurately has improved. Given that we know that since this improvement in technologies has been going on for hundreds of years, there's no reason to believe that it's going to stop today. So in future there will be even better, even more sophisticated technologies, and we will be able to measure even more accurately. So there is no real limit to how accurate something can get. We can only get as accurate as possible given certain circumstances. So whatever you've measured, it may be a very good measurement. I'm not saying that there's something wrong with the measurement. I'm just saying that inherently the accuracy is always subject to improvement. Okay, so that's the first part. The second thing to remember is that the word error, as used in this situation, is not really a reflection on uh, the goodness of the measurement, let's say. Uh, in other words, it's not saying that the measurement is wrong per se. What it's saying is that it's only as good as possible So the word error has a slightly different meaning in this context than it would normally have in everyday language. So here when we say error, all we are saying is that uh, that's our the measurement is the experimenter's best possible value, that they did their best and came up with that value, and so that value is subject to some kind of an inaccuracy, and that inaccuracy is being called the error here. So think of error as just a difference in the real measurement and the virtual or possible measurement that could have been if we had more and more and more sophisticated instruments. But it's not a mistake, so to speak. Okay. The third thing to remember is that errors in measurement, like we've already discussed, will always be there. It's not something that we can completely eliminate. Okay. But when you measure a single measurement, you get a certain amount of error. And if you were to use two, three, or four or more different measurements to manipulate a result, like in this case, we are finding the area of the sheet, but it depends on the measurement of length and the measurement of breadth. And so with two different measurements involved, the result is affected by both values, right? You have to multiply the length by the breadth to get the area. So both values are important. And so the error in each individual value will affect the final result. So that is also something to be remembered, that whenever we manipulate more than one value to find a result, then the error also gets manipulated alongside the actual or the measured value that we think is accurate. Okay, so those are the few things that I want you to keep in mind as a backdrop. And of course, if anyone has any questions that they need to clarify on this, uh, you can always get in touch with me and send me an email. I will give you an email at the end. In fact, I'm going to type it down right here just so it's available for whenever you need it. Will reduce to a lowercase if it will let me. Okay, so that is the email address right there. Or, for further clarification, if you have questions, if you need to know what I said, why I said it, and so on. Okay, so now let's go ahead and attack the question. The first thing is to set forth the operative formula, operative equation. And the equation in this situation that relates to our situation, when you have two values that are being multiplied, what happens to its uncertainty, or what do you do with its uncertainty? So this is how the equation looks. Delta y over y equals delta a over a plus delta b over b. Let's go ahead and define each of those terms so that everything is clear here. A is the length of the sheet in this question, which is 35.2 centimeters. B is the width of the sheet, which is 21.7 centimeters. Delta A is the error in measurement, which means that we've measured as best as possible. We think it's 35.2, but there is a possibility of a 20 centimeter error, which is a huge error. So in reality, it's unlikely that there would be that big of an error in such a small measurement, but that's beside the point. We're just using this as an analogy, as a uh, hypothetical to explain how to manipulate and find uncertainties. Okay, so delta A is 20 centimeters because it was given as 0.2 meters. And again, delta B is the same, and that is also 20 centimeters, which makes sense because it's the same person measuring most likely and using the same instruments. Okay, delta y is defined as the absolute error in the area. So once you do multiply the values and once you do take into account the uncertainties, the amount of error or uncertainty in the area, the total value of that uncertainty is given as delta y. Okay, and then y is of course the area based on the values measured, which is A times B from here. A is 35.2, B is 21.7, and it comes out to 763.84 centimeters squared. Okay, so the question is asking for relative error, and relative error basically means relative here is not like your uncle or aunt or granny. This relative is a comparison. In comparison to the calculated value of y, how much is the error? Okay, so based on that, what we are really looking for is just delta y over y. The entire ratio is relative error. So the amount of absolute error divided by the value obtained by multiplying the measurements or by taking the measurements into account, however it has to be multiplication, division, whatever. The ratio gives you the relative error. So if you look at this equation, the formula once again, um, the left-hand side is relative error because it's delta y over y. And then the right-hand side, you have all the values, so all you have to do is plug in and solve. So the relative error then works out to 20, which is delta A, over 35.5, plus 20 over 21.7, and that comes out to 1.49. And something you can verify by calculation, so I'm not going to go into the details of that. Math is not our focus right now. Our focus is the physics of measurement. All right, so uh, the value comes out 1.49, and the 20 in each of these cases is centimeters. The 35.2 and 21.7 are also centimeters. So in other words, delta y is measured in centimeters, y is measured in centimeters, and when you divide those two, the units cancel off, and so your answer, the 1.49, is a unitless ratio. So the uncertainty or the relative error in your area would be 1.49 given the parameters here in this question. Okay, so once again, if anyone has any clarifications that they require for this particular question, if they have any questions for me or if they have any insights, please feel free to email me on the website that I've stated. And I hope that you understand this and watch out for other videos on this and other topics in physics. Okay, this is Mr. A signing off.